right. Cool. Okay. At Beam Connectivity, we're working with 4 of our partners on the AutoCHERI project. So this is a business-led demonstrator project. So it's trying to deploy the sort of digital secure by design technology in the automotive domain. We've got a website there and an email address if you want to find out more information or fire some questions to us after this session. The session itself, so we've kind of split it down into 5 sections. The first one will be talking generally about the challenges in automotive and why cybersecurity is such a hot issue for us. The second is a short introduction to the AutoCHERI project, so what we're trying to achieve, what the main work streams are, and a bit on our progress through that. Then we'll get into some more of the sort of technical details, so looking at the operating systems that we've evaluated and where we stand today and which ones we're using. Then we'll talk about specifically how we ported our application to CHERI and how that's running. And then the last section will be about how we've integrated CAN networking into the Morello development box. And then at the end, we'll try and pick up any sort of Q&A which we haven't dealt with along the way. So if you do have any questions, feel free to put them into the chat, and we'll try and sort of deal with them as we go. But if not, we'll sort of circle back at the end. Okay, so first of all, talking generally about the challenges that the automotive industry is finding in cybersecurity. So there are a few kind of factors working against the automotive industry, in that the complexity of the systems that we're building into cars are significantly more complex than they were 10 or 20 years ago. So we've got things like a lot more wireless connectivity coming in via GPS and cellular, Wi-Fi and Bluetooth, and also dealing with things like over-the-air software updates, which bring a new attack vector into the environment. The software itself is far more complex than it was previously, so that complexity is going up. The supply chain is getting more complex. So previously we might have had a few layers of the supply chain delivering software. Now you have hundreds of individual companies or organizations supplying open source software, operating systems, hypervisors, machine learning frameworks. So the actual supply chain itself is a lot deeper and a lot more complex than it has been previously. I guess in line with most other industries, there are more vulnerabilities being found. So that's a product of both more people looking, both white and black hat hackers, but also the software being more complex means there are more likely to be vulnerabilities as well. And then finally, you've got geopolitical tensions, meaning that nation-state actors with I guess far more resources than other attackers are also looking for vulnerabilities and trying to exploit those. The graph at the bottom shows the average sort of lines of code in vehicles over the last 20 plus years, and you can see that now you've got kind of 300+ million lines of code deployed in a vehicle today. A lot of that will be in the supply chains, libraries, open source frameworks, operating systems. But the more lines of code there are, the more likely there are to be vulnerabilities in there, because programmers are humans, and humans make mistakes. So if we can improve the underlying frameworks and the underlying platforms that people are using, then that reduces the risk of vulnerabilities making it out into the field. A quick kind of primer on what a car is, and the network that a car is made up of. It's a much kind of used phrase that cars are now data centers on wheels. They're not single computers. They are 100+ individual electronic control units, or ECUs. Typically, each ECU performs a single function in the car. So if you want to put heated seats into a car, it's typically a seat with an embedded ECU within it, with its own software running on it. And all of these individual ECUs are connected via some kind of networking. And these are usually wired networks. So you've got CAN, which is the sort of dominant networking bus within a car. You've also got LIN, which is a kind of more simple, lightweight one. FlexRay is an automotive specific networking technology. And we're starting to see Ethernet come in as well, so gigabit Ethernet for really high bandwidth communications. And so that's today. You've got this vast network with big wiring loops going around the car. The future is all about consolidating from 100+ individual computers into 10 or fewer, much more powerful nodes with sensors attached. So, part of the rationale for doing this is that it's cheaper to consolidate your compute into one place. It also means that you can kind of load level your processing. So, certain functions only need to be run when the vehicle is off, the alarm, for example. So it can use the compute power which would normally be used for a different function when the vehicle is running. So you can actually sort of downsize your overall compute by centralizing it. It also makes things like over-the-air updates easier because you're not trying to choreograph updates across 100 ECUs in a vehicle, 100 computers. You've got far fewer individual nodes to update. So, the failure cases are kind of simpler because you're updating fewer individual things. But what this really means is that the individual software contributions from different companies that perform different functions need a layer of isolation because they're being co-located on fewer, more powerful compute nodes. And those individual workloads are, vary in their cyber criticality, their safety criticality, and their performance needs. So you don't want an infotainment system, a kind of music or video streaming type function interfering with a core safety critical system of the vehicle. So kind of isolating different workloads is really important. So the question that we're kind of posing is, how can CHERI help in this domain? Because there is a big change coming. And so can we apply this new technology to this area? This was a picture that I saw on LinkedIn the other week, and it's a Range Rover getting stolen. And it made me think that, most computer networks try and prevent arbitrary devices connecting in. So we have, in most enterprise networks, you've got firewalls, you've got authentication to make sure the device is trusted when it's connecting in, you've got access control lists. And a lot of this is perimeter security, prevent people connecting into your network. But it's really hard to do perimeter security when your users can just bust into your network at any point deep down. So this is really showing the need for kind of zero trust. So you shouldn't be implicitly trusted as a device or as a node on the network just because you're deep within it, because you could have broken through, like this picture here is showing. And part of the reason why sort of criminals are doing this is only some of the CAN networks support authentication or message authentication codes. Most of them are like unauthenticated. So if you inject messages onto the bus, you can make things happen without needing any secrets, any passwords, any keys to do that. I think another reason is there's a lot of poorly written proprietary network drivers, network CAN drivers out there. So they're not open source. They haven't been used millions of times, and they haven't had lots of eyes on them. They're just code that's deep down within the networking stack, which has been written for a very specific case. So all of this makes parsing untrusted data really key to automotive security, which is where memory safety really comes in, because you need to be able to know that when you're parsing that data, that you're not going to have sort of memory issues arising because of that. So that was kind of a bit of a primer on automotive security and automotive networks and why we think CHERI might be relevant in this area. Now I'm going to talk a little bit about the project specifically that we're undertaking with our partners. So we at Beam Connectivity, we make an end-to-end connected vehicle platform. So that's the hardware that we can see on the left-hand side, the telematics control unit, which is the control unit within the vehicle, which contains all of the wireless communication sort of radios. So it's got Bluetooth, Wi-Fi, cellular. And so what we're trying to do is kind of pose the question, what would happen if you replaced the hardware that runs on with hardware capable of running the CHERI instruction set? So making effectively a Morello TCU. And we're running that across, which we're trying out 4 individual use cases, which we support today. So we're looking at what happens sending telemetry data from the vehicle up to the cloud and over to a mobile app or an analytics portal. What happens going the other way when you want to send an over-the-air update down to the vehicle? You're doing kind of integrity checks, you're doing cryptographic checks on the package that's sent down. So how does CHERI manifest in that kind of workload? The third one is remote control or teleoperations, so remotely controlling the vehicle in some kind of way. So a simple use case there is locking the doors and unlocking the doors from your mobile app. So we'll be implementing that use case on the Morello TCU and understanding the impact there. And then the last one is it's new to Beam, and it's something that we're actively working on now, which is V2I, which is vehicle to infrastructure communications. So that is roadside infrastructure talking to the vehicle. This is rolled out across a number of cities and a number of test beds globally. And the specific message that we're looking at is the traffic light advisory one, which is where the roadside infrastructure, the traffic light tells the vehicle when it's going to change from red to green. That allows the vehicle to moderate its speed on cruise control so that you arrive at the traffic light as it's going to turn green, rather than having to stop and then start again. So it's a kind of efficiency and time-saving measure. And so we'll be looking at the implications on that use case of CHERI as well. So I think this is the last slide from me. So the whole project is split into kind of 3 broad categories or strands. The first is research, kind of desk-based research, so looking at the functional requirements of each of those use cases I just showed you, and then doing a kind of really deep TARA, which is a threat assessment and remediation analysis. So this is looking at, based on the requirements and the system design, looking at what threats there might be and what remediation, what mitigation measures you might want to put in place. Then we'll be looking at, how does CHERI play with those mitigations that are proposed? So does it work to mitigate a whole bunch of threats? In which case that's a real benefit of CHERI in that case. We'll then look at, or we are in parallel, I should say, looking at porting the TCU code base, so the telematics control unit code base that we've got already across to Morello. So understanding how much pain there is in doing that, what dependencies we need, that kind of thing. We'll then be implementing the new features. So that's really the V2I use case that I showed before. Then looking at benchmarking and comparing so that we can see what difference CHERI makes to those use cases. So is the performance impacted, for example? And then doing some kind of active attacks on that to see the mitigations in actually happen, right, in progress. Then the last thread of this is really looking at the market. So we know that companies don't buy technology for technology's sake. Change is expensive, change comes with risk. So what would make a company or an industry move to a new technology like CHERI? So we're looking at the benefits and the barriers of adoption in automotive. So trying to quantify those, trying to understand the market dynamics that would make this possible. Looking at the new automotive regulations. So there are a bunch of cybersecurity regulations that have been rolled out over the last couple of years, which particularly pertain to the management of cyber risk and vulnerabilities once the vehicle is out in the field. So how does CHERI impact the cost for a company to meet those regulations? So looking at that, and then finally looking at the route to market, because of course CHERI today is implemented in Morello in that's kind of a research grade platform, but there are a lot of steps to take it from having the instruction set to having an automotive graded module that we can put in a car. So understanding the players involved in that and the different layers of the supply chain to getting that technology out into the field is the last step, and then working out who we who we need to speak to, right, to kind of enable that and facilitate that move from research into actually in production. So now I'll hand over to Hardeep, who's going to talk a bit about the operating system choices that we've had.
Thanks, Rob.
Yeah, no worries.
So yeah, we gave a presentation at the last all hands DSPD meeting, and in that we showed a technology stack and informed people we were using Android. We received a lot of questions around that and why specifically Android. So we thought we'd go into a bit of detail about what operating systems we've tried, what they have, what were the benefits, what were the drawbacks, and getting up and going with using them. Just before that, I thought I'd give a quick overview of what the automotive industry looks like, so what operating systems they use, a little bit about where they're used. So there's a nice pie chart about cars on the road in 2021 in America and what operating systems they use. So as you can see, the yellow segment of the pie chart may surprise a few people. It surprised me when I first looked this up. And it's actually Windows Automotive. So it seems to have quite a large share, but that was delving a bit further into that. It turned out Ford chose to use a Windows embedded operating system from a little before 2000 to about 2015. But since then, it doesn't seem like very many people are choosing that. And so with their share of the operating systems used in cars is expected to reduce. Another point is that is only used in the infotainment of the car. So that's usually the center console. That might be the radio, might be sat nav, turning the heating on, basically just perhaps user interface rather than major operations of safety critical functions of the car. The largest segment of that pie chart is QNX. So that is an operating system offered by BlackBerry. It's used in both infotainment and telematics. Again, it's supposed to be quite secure. One of the reasons it's used in the infotainment is to try and protect people from getting to the telematics and other using the infotainment system to gain control of other parts of the car. As Rob mentions, cars usually have very many ECUs, so the ones that would be used to control the windows or perhaps the headlights, they don't quite need a full operating system, and they usually just run on microcontrollers rather than a microprocessor. And yeah, so what they would usually use would be a real-time operating system, maybe FreeRTOS or even bare metal applications, again, so people writing their own functions. The remaining two segments are Android and Linux. So Android, based on the research from this paper and the share that Android has is expected to grow, probably cutting into where the space Windows was having before, but at the same time, there's a lot of development being going into it, trying to make it automotive grade. So yeah, it seems like people are taking note and making the decision to adopt that. Linux, about a decade ago, also introduced automotive grade Linux. So that's the industry specific distro. So a collection of car companies, suppliers, and the Linux Foundation got together, decided, okay, what can happen to try and make Linux operating system of choice for these advanced features, such as mostly self-driving cars and assisted driving, where there's a lot more complexity in compute performance being required. So that brings us to Morello. and which operating system we wanted to go with. As Rob mentioned, we already have a TCU that currently runs on the Linux kernel. So porting that to Morello, we thought we'd go with Android again because that runs on the Linux kernel, to see what would be the to see what benefits that would bring and allow quite a direct comparison to what we currently have. It had the drivers we need, specifically CAN drivers, USB drivers, to get us up and running. We were quite familiar with it. We've done Linux development before, so it seemed like the operating system of choice. It has a number of other benefits. So ADB, the ADB bridge, allows transferring files, debugging and such. It just makes that a little bit easier, more user friendly. But there were some drawbacks of this, so it's not quite as mature in comparison to, say, Cherry BSD, which has a pure cap kernel. The Android Linux wasn't quite there, but what it did provide was a base that we could build our user application on. So as well as the drivers and that we use, most of our application dependencies are all in user space, so they could still be compiled and be made to work as pure cap applications. The advantages of Cherry could still be tested on that. So it was still good to a good operating system of choice. Another thing that came into consideration was the FVP. This is the fixed virtual platform provided by ARM. So it allows you to run simulations without needing the real hardware. What is reported by the FVP, if it works on there, it should work on the real hardware in the same manner. So that was great. It was a little bit slower. That's again in comparison to, say, QEMU, which is provided by the Cherry Build utility. The simulation on that was very fast. Again, that had the caveat that it may not be exact. Performance may not be exactly the same as performance operation may not be exactly the same as it would be on the real hardware. But we haven't really come across anything that behave too differently. Cherry BSD is a port of like FreeBSD, so not being based on Linux, it didn't have all of the dependencies that we needed, specifically the ones that were quite key to automotive. So Linux has been around and has been used in the automotive industry for a while. So it has the drivers built into the kernel. But speaking to Cambridge, they actually helped us out a lot. They recommended alternatives. Say for USB drivers, this does the equivalent operations in FreeBSD. Do you want to give that a go? And at the same time, any drivers that were missing, they're looking at trying to port over. So fingers crossed on that. There's many application ports available for Cherry BSD. You can see in the Git repo, in the GitHub repo, that there's quite an active community porting applications across. It gives other benefits of using that is just you can see what changes of the code occur to port something over to make it Cherry compliant. And suddenly taking those ports, you can recompile them and run them on Android or others. Other operating systems. There are other operating systems as well that are available, such as BusyBox. That's actually the one that we trialed out initially. So we started working on BusyBox, compiling C applications, trying out introducing memory faults, seeing if they would be spotted, and before moving on to Android. Just before Christmas, I saw that the latest version, Morello 1.5, had mentions of Debian in the user guide. So I think that's something that ARM are actively looking into, trying to port that over and get the Linux kernel working pure cap in that. But at the same time, if you don't want an operating system or bare metal is also supported, and there are instructions on how to get that up and running. So stuff we encountered, issues and benefits of we encountered when trying to get application running on Android. It offered C++ compilation, so I said we started with BusyBox. What we realized was the recommended, while that was fine for compiling C programs using like the Muscle C library and the Morello ARM64 development suite, it didn't offer C++ compilation. The recommended method was to use the Android system and the Android blueprint compilation. Android build methodology, which uses Android blueprint files, which is very good. We've not had any experience with it previously, anyone at Beam, but bringing that up and writing simple projects in it was very good. Had a lot of documentation online, and it's fine for new projects. But again, all of our existing dependencies and even our own build system for our application, they use more other build methodologies such as AutoComp and CMake. This proved a little bit annoying because you have the option to move all of your we were deciding whether to move all of our copying over the build methodologies into Android Blueprint, but we thought that would be quite a lot of chance of making mistakes. And some of these systems have quite large dependencies in their own, which they fetch and build. So it didn't seem like the choice that we wanted to go down. Static building is also required. Again, I saw just before Christmas that dynamic building may also be provided, but yeah, that's not something we've tried yet. The Android build system was quite interesting. It doesn't have a system root that you can just point at. So it actually contains a lot of individual libraries that get compiled, and the headers and actual library files get exported. And I think those get tracked. So when included in other projects, in other applications, they're just fetched, and the build and include compilation steps are made on the fly using the directories that are required. But to get around the CMake issue of having dependencies already using CMake or perhaps even AutoComp, we tried to use toolchain files that behave similarly to what Android was doing. It's not your standard toolchain file. It actually introduces a lot of include directories that you wouldn't normally. For instance, pointing to a system root, it tries to emulate that by pointing to all the individual libraries. And again, to accommodate the static linking, linking the libraries in the correct order. Something we did note is in our dependencies, some of them actually specified in their build files that they would like to be build shared and included. But so that might be something to look out for if you do want to change that to build statically. You may need to go into the build files and change them. CHERI-BSD, we also looked at the CHERI-BSD operating system, which is instructed to be built using Cherry Build. It's actually a really good application. It makes everything very easy, whether it's a compilation of repositories which have either been community ported or your own. You can introduce it. You can write a Python script to try and get it to build your own repository too. At the same time, it also makes building disk images, whether it's for simulation or flashing onto a USB stick and putting it on the real hardware, it makes that very easy too. Cross compilation is more standard. You can have a standard toolchain file and point to a system root directory, set your architecture that you're trying to compile for. Yeah, and get that up and running. PureCap and ARM64 versions can be built, which allow comparisons to be made using the exact same operating system, the exact same files, just compiled slightly differently using different different compilers, and yeah, using slightly different compiler options. There is also hybrid. We haven't looked too much into that. Being a user space application, it wasn't too difficult, as I'll show in a minute, in porting the code section, but it wasn't too difficult to port our code to be fully pure cap. So we thought it would be easier than taking the intermediate step of going partially pure cap and leaving what we could import as regular ARM64 code. But as we said, CAN drivers weren't present. But to get around this, we wrote an SL-CAN application. So that's a serial line CAN application. Serial line CAN is a protocol to communicate CAN dongles. I think it's given in the, I think it was specified by it's specified in the Linux kernel. I'm not sure where the actual specification comes from, whether it was a manufacturer that that decided on it and it was just adopted, or whether they suggested that this is how communication should occur. But you can find out information about serial line CAN online and get that up and running. It's not too difficult. So you can talk to your dongle just via USB serial communication, reading and writing raw CAN frames. With that working, we were actually able to have our application working on both Cherry BSD and Android, and just with being user space, just changing the toolchain files and having a build system that could build for both, we were in a comfortable place to work on both platforms. So that was about the operating system, and now I'll go on to actually porting code to Cherry. So I have a couple of examples that we actually went through, delve into a bit of detail about perhaps decisions that were made, and what they have on the impact of the long-term porting of code to Cherry. I thought I'd just give a quick overview of our experience so far. So I'd just like to point out a statistic in a presentation given by Alex Richardson for those who are at Cherry Tech 2022 in London. He's ported a lot of code to Cherry, and one thing that kind of stood out from his presentation was on KDE on X11, only 0.026% of the 6 million lines of code needed to be changed to get it to compile and run on a Cherry compliant system. That is a tiny amount. So I think fewer than 2,000 lines of code out of 6 million is actually really amazing. But I think that goes down to how Cherry has been thought up of from day one. It was intended to be compliant to C standards, to not require significant changes to code, and code that perhaps didn't make assumptions that aren't specified in the standard. So assumptions that are really usually of types of variables. If they weren't made, it's most likely that the code will be able to compile and work without any change at all. But there are perhaps not erroneous code, but code which didn't think about or expect Cherry to arrive. And there are typical coding methodologies and decisions that were made that need to be accounted for. A lot of these decisions are well known, and looking at the Cherry C++ programming guide, it informs you of a number of issues that you will probably face when porting code. Again, some of these examples might include assuming that a long type is enough to hold a pointer, or even a pointer difference type. But these aren't strictly stated in this. I'm guessing they're not strictly stated in the standard, and no longer true. When you do start compiling code to be Cherry compliant, you'll use the LLVM compiler, and it actually produces a lot of warnings. So before you even get to running your code and trying to find out if there's a bug or not, these warnings you'll be able to make the change before runtime for expected issues that are going to arise. I think again this compiler is really good, even if you're if you're not planning on running the program in Cherry, because it stops you making assumptions. Again, specifically those of converting between integers and pointers. But yeah, when you do actually make the changes in the code, as I said, the number of changes are very minimal, but at the same time, the changes that do take place are quite simple too. So majority of the time, it was just changing a type, whether it be from a long or a point difference type to an int pointer. But as you'll see in a minute, sometimes decisions have been made that pointer difference is the type people choose for, whether it's to maintain compatibility with older standards or various other reasons. The one place where we saw the compiler not being able to help out were memory allocations or memory allocators. And again, they were written without the expectation of Cherry, probably along with the majority of the code that was written. And so when alignment is up, pointers need to be 16 byte aligned. Sorry, capabilities need to be 16 byte aligned. If that isn't the case, it won't be able to be dereferenced. So although the majority of code, this is fine, such as when you allocate a block of memory for a structure, it would be able to align all the pointers correctly, as well as the other variables. But when people start to write their own memory allocators, either for debugging or to include extra information, it kind of starts throwing the alignment off. So what we've ported to Morello, you can see on the right. I think this was shown at the DSPD all hands presentation again. So I thought I'd just quickly go over it. There are a number of dependencies that were community ported, so SQLite, OpenSSL. Other really common dependencies we actually compiled ourselves. This was before we realized there was a large GitHub repository of ported code already. So zlib and canutils we ported ourselves. They actually required no change at all, so it was just a recompilation. Once we had a build system, a build flow working in the toolchain files, that was actually they just worked straight off the bat. Others, such as JSON-C, Boost, and DBC, PPP, fixing the errors pointed out by the compiler, so fixing the warnings pointed out by the compiler, just double checking that they are real warnings, resolving them if they needed to be resolved. Got them working. But others, such as libxml2 and payho, the number of changes required there were a bit more significant, either mostly due to alignment issues. So it wasn't always at the compilation stage that we found out that issues that it was Cherry compatible. After actually running at runtime, we had tag faults or bus errors, and they need to be resolved using the debugger. But yeah, again, our TCU application required minimal changes too. So what peripherals do we have working? We managed to get a CAN bus adapter, a CAN bus dongle that we could that would plug into the car or our laptops for simulation. We got that up and running. A GPS reader, as well as a 4G cellular modem. Being a TCU, we needed to communicate wirelessly. And then, so once we got all them up and running, we got our Hello CAN bus, an application which is like the Hello CAN world, just sending CAN bus data. Again, repeatedly at every stage, introducing bugs to make sure they still get detected, seeing what can learn about Morello as a whole and the CHERI architecture. MQTT communication with the cloud service. So when we read data from the car, we could send it to the cloud. Again, that goes via the 4G cellular modem. That once that's set up, we can allow all the software updates to test our application updating, and yeah, move on to remote commands such as sending a signal from the cloud to unlock the door of a car. What we're working on now and over the next few months is the vehicle to infrastructure stack. So trying to get that up and running in a CHERI enabled environment. So this was a screenshot of an issue we resolved in libxml2. So the file that was proven problematic was parser.c. So when we compiled the dependency, the compiler produced a warning, which is a cast from an integer type to a pointer type. You can see the warning that was produced in the top right. Yeah, as you can see, the variable the variable initially gets casted to a point diff type and then casted to a void pointer. It's interesting when you see what the actual function does. So the XML hash add entry, looking at that function, expects a context, a couple of names, but the offending function argument is the last one. Under normal use cases of this function, it expects a pointer to use the data, which can then be fetched at a later date, dereferenced and pointed, and then used to retrieve the original data that you wanted. But in this specific case, where it's storing the variable type and initially casting it to a point diff type and later to a void pointer to as the function would require. It wasn't storing the addressive type, but the type is actually the pointer is actually storing the value of the data itself. The pointer value is the data itself. So instead of requiring a dereference, once this is fetched, the actual value that is returned from the hash fetch function would be used without dereferencing. So although this would work on a CHERI enabled system, it's probably best to try and clear the warning so your logs don't get flooded and you can actually focus on what is of importance. So changes this from a pointer diff type to an integer pointer will make the cast correct. And although the tag bit to allow dereferencing of the pointer may not be correct, it doesn't necessarily affect the operation, as the return value would never be dereferenced. I picked this one specifically because I noticed the git commit message when this line was last changed. So before being changed to a pointer difference type, it was originally a long, and this produced a compiler warning because on 64-bit Windows, it's a long type is 32 bits and can't hold a pointer value of 64. Again, it doesn't affect digging into the code. The type variable that is passed on is actually is an enum, so it actually only contains values of 0 to 7, so that would have been problematic. But the decision was made to clear the warning. It goes into a bit of detail about why int pointer wasn't used again. So pointer diff was. So it was a known assumption that pointer diff would be the same size as a pointer would be, and at the same time, without requiring C99 types, it would allow compilation. So the writer of the code actually made the active decision to use pointer diff rather than what would have been more suitable, such as int pointer, to maintain that older compilation standard for compilers that aren't yet running later standards. A second example of pointer changes that we had to make was in the payhole library, so payhole mqtt, specifically the file source.c. There was no compiler warning to come with this. It was a runtime error that occurred. It came out as a bus issue, but once we had our debug working, got that up and running in a convenient way, we could see that the offending file was source heap.c, which, as you can guess by its name, it's actually redefines the operations of memory allocation. So instead of calling the standard malloc, you could see the code highlighted in blue in the code snippet there. It instead it expands your requested allocation, which is variable size, as you can see in line 199, and it increases it by the size of iCatcher, an iCatcher type, which it sticks at the start and the end. This is specifically for debugging. So the return variable, when it comes to being freed or later on during operation, checks are done to perform that the iCatcher value, which is a value of known type, has not changed, and that's an attempt to ensure that you have it written outside of the allocation, accidentally overflowing it or anything like that. So you can see the code, but in short, you can see the diagram at the bottom, which is a visualization of what the code's trying to do. The original call to malloc would return a pointer on the very left at the start of iCatcher, but the pointer that gets returned to the user application is the requested allocation size, the start of the green block. So that would have an offset of iCatcher. And then again, looking at the top right, you can see that iCatcher is just a type def of what it was originally was double. Again, the assumption that pointer and double have the same alignment, but it wasn't the case. That's not the case for Cherry, one being 8 bytes and the other being 16. Changing it to integer pointer type resolved it and got it working, but again, assumptions were made when the code was originally written that are no longer true. In both of these cases of explaining porting code, the assumptions that were made were actually stated in the programming guide standard, the Cherry C and C++ programming guide. So none of this was quite new to, and all of the issues that we've seen have all been stated in that guide. So that probably is a very good place to start reading if you are looking at porting code to Cherry. Yeah, I think that was a quick overview of some issues that we faced when porting AutoCHERI, common ones that may be faced by all. So now I'll pass over to Sam Dudley.
Yeah,
talk about CAN.
Just quickly on that previous section, a couple of questions. CHERI's capabilities and memory bounds checks would prevent this from needing to have the eye catchers. So yeah, these functions are actually redundant now. But
sorry, I should have mentioned that. This HeapC and this memory the memory allocation protection debugging method of introducing these eye catchers, if you do have bounds of the correct type, it's no longer needed, because you would get a capability tag fault, not a tag fault, sorry, a bounds fault. So yeah, you don't actually need this debugging method anymore.
Great.
Any other questions? Or should we leave it to the end? I'll let you move on. I'll have a quick look at the chat.
Yeah, so implementing CAN on our actual Morello system. Go to the first slide, please. So as Hardy touched on a little bit, under the Android system, we had the correct drivers for CAN. So it was a nice, easy kernel space drivers and then a user space application, how we would normally expect to do it. But then on CHERI, those CAN drivers weren't available. But because our CAN transceiver was a serial device, we were able to write an application layer to sort of read the serial and then sort of create the CAN packets. So yeah, currently we have a user space application and driver, and then just the serial drivers in the kernel space. We're talking with Cambridge currently, and hopefully soon we'll have the CAN drivers in the kernel space, and we'll move back over to the left-hand diagram on CHERI as well. So on Android, it's very straightforward to turn CAN on. Obviously here we've just got this serial CAN interface in the build Linux script. But if you wanted other CAN devices, vCAN or like the PEAK CAN devices, you can also enable those. So yeah, very straightforward to turn CAN on under Android. And then yeah, so we get to the sort of setup we have. So going from the right, you've got the Morello box with a little Wi-Fi dongle in, USB connection to our CAN device, which someone asked earlier is a USB 10 we've been using. And then what you may have seen previously from our previous demo, it goes into another USB 10 and then into a laptop or similar device to emulate the car signals. And then what we've moved on to more recently is going into an actual vehicle, which is the desired solution. But we can't all fit vehicles in our offices, so we've got to come from a laptop for most of our testing. So yeah, this is the setup we had at the last all hands meeting. The box in the bottom right is our vehicle simulator, and it just pumps GPS data and various faked sensor details over to the CAN transceiver, and then the Morello handles that and does all the computing on those signals to figure out what they are and sends it all up to the Amazon web server. And we then receive those on the two devices on the left, so the mobile, to give you a nice like a map of where the vehicle is traveling and all the information, and then analytics portals to sort of monitor things over time. So then we came to try and put it into the actual vehicle, and we hit another snag. So body bus of our vehicle was a low-speed CAN, whereas the USB 10 was a high-speed CAN. And by this point, we'd migrated onto CHERI, so we didn't have the option to sort of swap dongles and go onto a different CAN device. So we had to try and figure out a way to make the USB 10 work with low-speed CAN. It turns out the transceiver actually on the device is tolerant of low-speed CAN. So with a through a resistor mod, we were able to get the USB 10 talking at low speed. But then there was also an off-the-shelf solution we found from PEAK. So a nice, easy, just connect it in line, and it'll do all that hard work for you. So on the next slide, these are some scope traces and some sort of expected outcomes of what you'd expect for a high speed versus low speed CAN. So the main difference is in low speed, the recessive state is pulled to either rail, and then whereas in high speed, your recessive state is at the same level, so 2.5 volts. In low speed CAN, it's also called fault tolerant CAN, and that's because there is a larger acceptable voltage on the CAN lines. So that was sort of something just to watch out for, making sure we weren't going to blow up any devices. And then we finally get to actually putting it into a vehicle. So we ended up going with just the PEAK connector, which you can see on the top left, because it involved less changes to the components we've already bought. So yeah, we connected the PEAK connector directly to the vehicle bus, and then that into our USB tin, and then ran the USB through the car into the boot, where our Morello was set. And so, yeah, in the big picture, you can see the Morello set in the boot, a lot of power leads and a lot of mess, really. But eventually, we're hoping to shrink down the size of the Morello box, swap it into a smaller case, and get it into a bit more of a manageable state, and run the main supply from the vehicle, not from an outlet. So having that all wired up, we managed to get in the car and then control the locks and read the car sensor information, and sort of get to the point where we actually were acting as a proper TCU. So then we start looking for what's coming next. Next slide, please. So one of the things we want to do is stress test the CAN bus and sort of compare pure CAP application against a non-Cherry capable application. If we can get both running on the Morello, then we should be able to see side by side what impact making an application pure CAP is having on performance. Obviously, we want to swap the user space CAN driver to a kernel driver. Although we do have it working, there are some benefits of having the kernel driver, and we should be able to sort of use the kernel buffers to sort of manage our data flow a bit easier, and it will make their application compatible across multiple operating systems, where now our application is different on Cherry BSD because of that extra little block. And then we also want to start trying to introduce the vulnerabilities and exploit them and see where Morello and Cherry can protect from. And then that moves us on to we're going to do some fuzzing of our application again, try and see where the securities lie, on where it fails. And then, as mentioned before, we've got our V2R use case. So we're looking at Glosser, which is green light optimized visa advisory, just to sort of add that new technology and see if Cherry makes any difference to that. Rob, I think it's back to you.
Yeah, this is kind of the last slide, really. We've managed to sort of get through all the content in pretty efficient style. So I guess I'd welcome any questions at this point. I see one has just popped in. I know it's quite good, actually. The community is working well because you're answering each other's questions, which is great. It saves us a job. But I don't know if anyone's got any questions they either want to drop into the chat or just unmute yourself and shout it out. We can try and deal with them now.
Yeah, so thanks, Brian. Hopefully the Cherry memory guarantees does make the eye catcher redundant. Again, that was in the Payhole library, that was purely for debugging. So before Cherry was a thing, they needed a method of checking how if memory allocations were overwritten, and so that was what they chose to do to track it.
We've got a question that's come in about vulnerabilities that we might try. So we'll be working with the University of Exeter to do some kind of white box testing of the system. So they'll have access to the source code. They'll try and find vulnerabilities and exploit them. A typical one, which I'm expecting that we could find, although I hope not, is unexpected CAN messages or oversized CAN messages or messages from the cloud that we don't expect. So we'll try those, and actually, if we can't find any vulnerabilities that we can exploit, we may well introduce, purposefully introduce some memory vulnerabilities into our CAN drivers or our cloud message processing code, just to kind of experience what the difference will be, between running sort of pure cap and running as just sort of vanilla. So yeah. I think that is it then. There's been no new questions for a couple of minutes. So I guess if anyone wants to follow up with us, then the email address is up there. That will be routed through to myself and the team, and we'll try and publish some updates on the AutoCHERI website, which you can see there, autocherry.tech. And yeah, looking forward to some kind of follow-up presentations from other organisations within the community soon. Darren, I don't know if you want to say anything.
Yeah, thank you, Rob. Yeah, cheers for that. So Rob and the guys from Beam kind of approached us after the all hands and offered this kind of this session to the community. But I just wanted to open it up to others, I suppose. Anybody on this call, anybody who's kind of got one of the projects running and would like to share kind of some of their lessons, some of the things that they've been doing, then feel free to get in touch with either myself or George, and we can facilitate this session as we've done with Beam today, so we can kind of put it out to the community, set up the Zoom and all of that. So if there is something you'd like to do, something you'd like to share, something you think that other people should probably hear and can learn from, then please do get in touch with us, and we can help set up that session. So yeah, I'll just leave you with that, I guess. But yeah, thanks once again to Rob, Hardy, and Sam.
Thank you. Yeah, thanks everyone. Have a good rest of your day.